Welcome to today's Explainer. I am so incredibly thrilled to take you on this journey. We're going to embark on a massive zoom in, starting all the way out in the tangible physical world we can actually touch and feel, and we're traveling all the way down to the hidden, microscopic biological scale. It's a journey of perspective, precision, and honestly, the beautiful architecture of nature itself. So let's jump right in.
It's a fascinating thought, isn't it? From the staggering width of an entire galaxy, down to the programmed death of a single microscopic cell inside your own body, how do we actually measure the rules of nature? Over centuries, we've built some wildly ingenious tools to comprehend the vast and varied scale of the universe. And understanding how we measure these extremes is literally the key to understanding how our own bodies work and how the universe around us functions.
Section 1. Language of the Universe.
Okay, let's dive into this. To understand how we measure things, we first have to understand the foundational language that dictates the rules of everything around us. And that, of course, is physics. You can really think of physics as the mother of all sciences. It's the branch of science that observes nature, represents it mathematically, and concludes with experiments. It basically gives us a pragmatic set of rules with a truly beautiful architecture that governs everything. Whether you're looking at the spin of a tiny atom or the orbit of massive galaxies, physics is the tool set we use to decipher the whole shebang.
Section 2. Measuring the physical world.
So let's see how this builds our understanding of the tangible world. To apply physics, we absolutely have to capture and quantify these physical laws using specific, standard measurements. The completely crucial point here is that all physical phenomena in the universe can be quantified using just 7 fundamental physical quantities. We're talking length, mass, time, electric current, temperature, amount of substance, and luminous intensity. These are the absolute building blocks. Every single other physical measurement you could possibly think of, like volume, velocity, or density, is a derived quantity born directly from these magnificent 7.
Now let's focus on length for a second, because arguably length has proven to be the most useful measurement for humanity throughout our entire history. The standard SI unit for length is the meter, and for everyday tasks, a simple meter rule is incredibly effective. It's exactly 100 centimeters long, and it's divided up so that it can accurately measure down to a single millimeter. But in the grand scheme of physics and engineering, 1 millimeter is sometimes just way too big.
And this brilliantly illustrates our drive for precision. Enter the micrometer screw gauge. This tool is extensively used in engineering for getting extremely precise measurements of very small dimensions. To use it, you just grip the object between the anvil and spindle, turn the ratchet until it clicks, take the main scale reading, and add that to the thimble scale reading. It works on the simple but genius principle of converting tiny, barely visible linear distances into much larger, easily readable rotations of a screw.
But here's where it gets really interesting. A screw gauge is fantastic for a thin piece of wire, or, say, a tiny metal ball. But what do we do when things get even smaller? How do we measure what is fundamentally too small for a mechanical screw gauge? How do we measure the building blocks of life itself?
Section 3. Scaling down to micro. To understand the unseen, we actually have to shrink our perspective, both mathematically and biologically. To pull this off, scientists use SI prefixes as a sort of mathematical passport. While a prefix like kilo multiplies our unit by 1,000, notice how prefixes like milli, micro, and nano allow us to fractionate down to 3, 6, or even 9 decimal places. This is exactly how we accurately document and mathematically enter the unbelievably tiny world of cells, DNA, and atoms.
Section 4. Tools of the Unseen.
Of course, mathematical scaling is really only half the battle, right? When we shift our focus to biology and these crazy microscopic scales, our traditional physical tools, like that screw gauge we talked about, become completely useless. We need entirely new observational tools. And the evolution of human vision here is amazing. We started with early, historical wooden microscopes that honestly look like beautiful antiques and evolved all the way to modern, highly complex metal microscopes where our observational power has absolutely skyrocketed. But there's a vital rule of optical physics to remember here. Modern microscopes require both high magnification and high resolution. If you only have high magnification but low resolution, well, all you're going to get is a bigger version of a blurry image. You absolutely need both to truly see the microworld clearly. Now, what's really fascinating is that once we finally peered through these high-resolution lenses, an incredibly diverse, organic universe was revealed right inside of us. We discovered that living organisms are made up of beautifully diverse tissues. We could suddenly visually measure and identify the smooth muscle tissue that lines our organs, the complex web of nervous tissue, and the incredibly structured pillar-like columnar epithelium,
It's an entire bustling universe happening inside us, totally invisible to the naked eye.
Section 5. Cellular Life and Death.
Okay, let's zoom into the absolute maximum now. Just as there are strict laws of physics governing the macro world, like gravity acting on a falling apple, there are incredibly strict rules governing the building blocks of life in the micro world. It turns out cellular activity is highly programmed. A cell in an organism doesn't just do whatever it wants. It relies entirely on incredibly complex cell signaling mechanisms. Think of it like a microscopic postal service. Cells have specific receptors on their surfaces that receive chemical messengers or extracellular signals from their environment. These cell signaling mechanisms dictate everything a cell does, from when to divide, how to act, and fascinatingly, even when to die. It's a constant microscopic communication network ensuring the whole organism functions as a unified whole.
And when it comes to cell death, there is a stark, dramatic contrast in biology. We basically have two main pathways, apoptosis and necrosis. Apoptosis is what happens when those extracellular signals tell a cell its time is up. It is programmed self-destruction. It's tidy, controlled, and purposeful. Necrosis, on the other hand, is the exact opposite. It's accidental cell death caused by external factors like a nasty infection, a dangerous toxin, or a tumor. It is chaotic, completely unprogrammed, and super messy.
Let's look a little closer at apoptosis, because it is just mind-blowing. It's officially defined as a programmed change leading to a sequence of physiological changes by which cells commit suicide collectively. Now, you might be wondering, why on earth would cell suicide be a good thing? Well, programmed cell death actually helps control proper multicellular development. For instance, believe it or not, when you were a developing human embryo, you actually had a tail. But apoptosis deleted that entire structure. It also gracefully deleted the unneeded webbed tissue between your developing fingers and toes. Without this carefully measured, highly signaled self-destruction, we literally wouldn't develop properly.
And that brings us to the end of our incredible zoom-in. We've traveled from the precise turns of a mechanical screw gauge all the way down through the lenses of high-resolution microscopes to witness the programmed death of a single cell guided by microscopic signals. It really makes you wonder, as our tools for measurement continue to evolve, how much more of the universe is waiting to be discovered just beyond the limits of our current instruments. Keep that curiosity alive, and thank you so much for joining me on this explainer today.